Hello, everyone. Thanks for taking the time to be here today. My name is Caspar Stinn, and I'm going to be talking about our new technology to decarbonize metal production. So I work with Professor Alanor here at MIT in the Department of Material Science. So when we look at metals and mining today, there's a significant decarbonization challenges facing us. So right now, metals and mining account for 10 to 30% of global emissions, depending on how you do your accounting. And when we look at the breakdown of the emissions within metals and minerals, you can really be broken into two groups. There's your steel and ferrous components, so things that pertain to the steel industry, and everything else. I'm not going to be talking about materials related to cement, because those are a separate challenge, but just focusing on minerals and mining as they apply to metals. So when we look at technology that's available today to decarbonize metals and mining, as well as some of the alternatives that are emerging on the market today, they really don't meet current needs. So we have the conventional tools in our metals processing toolbox. We have carbon-based pyrometallurgy, water-based leaching, and then we also have some new emerging specialty chemistries, bio-based leaching processes. However, if the goal is to decarbonize, conserve water resources, and develop new scalable materials economy, we really need to bring about a new metals processing paradigm. So with that, I'm going to be proposing a new process chemistry where we're working on to economically decarbonize metals production. And this first begins with the material separation step. So when we look at production of metals, they come from a variety of sources. You can produce metals, say, from an ore or a rock you dug out of the ground, or maybe you're recycling, looking at processing something like e-waste. In either case, you start with something that's a mixture of a lot of different metals, where you're normally interested in producing separated metal compounds of value. So what we do is we start with our mixed metal source. We go through some of our new process chemistries and reactions. And what this actually causes to happen is the metals that were in this source to actually separate into distinct physical phases. Once you have the metals partitioned into phases using our new process chemistry, you can conduct physical separation to get separated metal compounds. And this approach is applicable in both mining and recycling. So this is an example of how we used this approach to recycle batteries. So this is a battery cathode that we treated with our new process chemistry, which caused the partition of valuable elements into distinct phases. So starting with this mixed battery cathode material, we separated the elements of interest, the lithium, nickel, cobalt, into distinct phases, which could then be separated for remanufacturing of battery. We've done the same approach for magnets. So again, we started with a magnet, we conducted our processing approach, and we formed separate phases, which you can see here, the different colors in the material. Once these elements within the magnet are separated into separate phases, they can then be used for remanufacturing of a new magnet. So this is on the separation step, the first step to decarbonizing metals production and what needs to happen along the value chain. Following metal separation, though, you get separated metal compounds. These pure metal compounds, of course, need to be converted into a metal end product. So to do that, we've developed a decarbonized metal production pathway, where we can take these metal compounds, we can conduct reduction to convert these compounds into metal using carbon-free chemistries, and these carbon-free chemistries then enable the production of metal alloy products that integrate with existing value chains today. So we can produce metals from mined or recycled sources. So here's an example of two steel and ferrous-based products we made. This is an iron rare earth alloy for magnet production that was produced from an end-of-life magnet. Here's an example of ferronickel. So we can produce ferronickel from, say, mineral sources or recycling sources. And this is used as a component in stainless steel production. We can also make aluminum products. So this is an example of aluminum manganese alloy or scandium aluminum alloy. So it's really applicable across a wide range of metals processing challenges. We can really think of this as a platform technology for decarbonization in metals production. But beyond decarbonization in metal production, there's also significant cost savings that are achievable using a new process-based chemistry. So when we compare our approach versus conventional hydrometallurgy from a capital cost perspective, we see that the capital cost can be reduced by about 65% using our technology. Looking at operating cost, I have a case study here for stainless steel production. The conventional operating cost of producing a ton of stainless steel via the legacy pyrometallurgical route is about $2,100 per ton. With our new sulfur-based process chemistry, we can drop that down to $1,300 per ton. So in addition, there's significant cost savings achievable both on the operating and the capital perspective. Looking at where this fits in from a sustainability perspective, like I said, depending on how you do your accounting, your global greenhouse gas emissions for metals 10 to 30%. When we look at the reduction that's achievable via our new process-based chemistry, we can actually reduce that substantially. So looking at the total environmental impact of the metals sector today, applying a new sulfur-based process chemistry across the board, you could potentially reduce global emissions by 10 to 20% using our technology. So where we're at and how you can help. So right now, we've developed a pilot scale reactor that's operational at MIT. It operates at a scale of 1 kilogram per hour. So right now, we're looking for partners for deployment, as well as possible opportunities for funding. So if any of this is of interest to you, please feel free to stop by my poster later, and we can have a discussion. So thank you very much.